The topic is about the CAN protocol. Here, the CAN stands for the Controller Area Network. And coming to the topics, that to brief about the CAN protocol, so understanding the overview of the CAN protocol and CAN protocol layers, message structure, how that messages will be transferred between the devices or between the ECUs, and the types of the CAN and CANBus topology, CAN communication characteristic, CAN protocol version, CAN bus application version, advantages of the CAN and limitations of the CAN, and how this CAN protocol is used in the embedded system, and the development tools, and CAN versus other protocols difference, and what are the common use cases that available in the CAN protocol. So coming to the overview of the CAN protocol, so it is used for the communication between the ECUs or the nodes without any central host should be available. It is a message-oriented CAN protocol where data will be transferred uh, between the ECUs, and specific to the message-oriented protocol, and it ensures that data will be transferred and it will be maintained in the HARS environment, and it make it ideal for the automotive system like engine control transmission or airbags or any anti-lock braking system ABS. And the CAN protocol layers, it will be the data link layer or the physical link layer of the OSI model. Physical layer, it defines the electrical and timing aspects of the network, including the signaling level and bit timing and the physical medium with the twisted pair cables. And data link layer, it handles the message framing, arbitration, and error checking and acknowledgement. So this layer ensures the reliable communication and manages the collision between the messages from the different nodes. The message structure of the CAN frame, so where the data will be transferred within the network. Here, this will be the tools where used to monitor the CAN messages on the specific development tools or the testing tools. So it includes the messages and the IDs and the timing. So to understand about the message structures, how the data will be transferred, the first phase will be the startup frame, SOF we call it identifies the startup frame. 0 stand for start sending the messages. 1, there will be no message will be sent. And coming to the arbitration field will be the next frame, and it have the identifier. Based upon the ID, the message will be transferred. So we have two different types of identifiers, 11-bit identifier and 29-bit identifier. And in arbitration field, we have the remote transmission request, we call as RTR. It indicates whether the frame is a data frame or the remote frame. Next will be part of the identifier extension, we call as IDE. So it indicates that IDE field is 11-bit identifier, means it will be a part of a 0, and 29-bit identifier, it will be a part of a 1. So we go in detail in the frame format to understand about what is the identifier extension and what is the remote transmission request and what is the identifier. And next will be part of the control field in the message structure. So here it decides how many bytes of data that we are transferring in the message. So here the data length code DLC, it indicates the length of the data payload in the bytes. And control bits field consists of 4 bits, which indicates the length of the data field. It will be a 0 to 8 bytes of data. And data coming to the data field, the field contains the actual data that being transmitted, and it will ranges from 0 to 8 bytes, depends on the control bits. And we have the CRC field. CRC field will be the cyclic redundancy check. It is used to it's specifically used for the error checking, and where the messages will be efficiently transferred. It is calculated based on the content of the data field. And here the CRC slot, it checks used to detect the errors in the frame. And CRC delimiter is always the recessive, and it in CRC delimiter, it is designed this to provide the consistently synchronize the data and the separation between the CRC slot and acknowledgement slot in the CAN frame. And coming to the acknowledgement field, acknowledgement slot is a acknowledge of the message transmission by the receiver node. So here, transmitter sees the dominant, the message was acknowledged if it remains recessive and no node acknowledged the message. Dominant 0 if the receiving node successfully received the message and has no error to report. If the receiver node correctly receives the frame after performing the CRC checks, if it changes the acknowledgement slot from 1 to 0. Here 1 is the recessive state and 0 is the dominant state. And coming to the recessive 1, if the receiving node detect error in the receiver message, the remote frame, it will send the recessive 1 in the acknowledgement slot. A dominant level in the acknowledgement slot represents a positive acknowledgement, while a recessive level indicates the negative acknowledgement. An acknowledgement delimiter is the always say recessive during the transmission. It serves as a separate between the acknowledgement slot and the next field in the CAN frame. And finally will be the end of frame. It identifies the end of frame. It is a sequence of 7 bits, means here it will be always recessive, the ones, 7 ones. So in the frame, this will be the end of the field where the frame message will be ended. So these are the 7 fields, the message structure in the CAN where it will carries the data. So to understand in detail, we will go in specific fields of each one in the coming slides. And between each messages or the frames, we have some space or the delay we called as a interframe space. It will be a part of IFS, a sequence of least 3 recessive bits, and it will be the signaling the space between the end of one frame and start of the next one. And we have 2 types of CAN. There are standard CAN frame and extended CAN frame. So based upon the identifier, the 11-bit identifier stands for standard frame, and the extended CAN frame, it will be the 29-bit identifier. So here the 11-bit talks about 8 bytes of data that can be transferred, and extended CAN frame, it stands for 29 bits of data transfer. 0 to 64 bytes can be transferred in the extended frame. So to know in detail about what is the standard CAN frame, so as we discussed, the message will be transferred in the form of frames. So the first field will be the start of frame. It will be the 1 bit. So here 1 bit will be always 0. So to start any messages, if there is no message is transferred, that time it will be the 1. And coming to the arbitration field will be the 11-bit identifier, and we have the ID identifier extension, and OTR will be the 1 bit. And next will be the part of the control field. So control field will be the DLC. Here 2 bytes are reserved, and next will be the 4 bits. So based upon the 4 bits of the data, whatever the data we are going to transfer in the terms of bytes, that will be decided based on the control field. Next, we'll be having the CRC field. In the CRC field, we have the CRC slot and CRC delimiter. So CRC slot, it will be the 15 bits of the data. So whatever the data we transfer, so that will be calculated, and DRC limiter will raise the acknowledge of the data that is error or not. And coming to the acknowledgement field, it will be the acknowledgement slot and acknowledgement delimiter. Acknowledgement slot will be the 1 bit, and acknowledgement delimiter with the 1 bit position. And end of frame, it will be the 7 bits. And we have the IFS, so it will be the part of the interface frame. And it is generally this standard CAN frame is suitable for the applications where the smaller identifier is sufficient, and it supports up to 2 power of 11, means 2048 unique messages identifier can be configured for this CAN frame network. So generally used in the simple system and with the lower messages requirement, this CAN frame can be used. And coming to the extended CAN frame, so here arbitration field, we have additionally the SRR. SRR will be the 1 bit, and coming to the RTR will be the 1 bit, and additionally we have the 18 bits identifier. So standard and extended. So the main difference will be stands in the arbitration field. So in arbitration field, we have the 11-bit identifier, SRR 1-bit identifier, and IDE 1 bit, and 18 bits identifiers, and the RTR will be the 1 bit. And control field, we have the 2 bits, and 4 bits. So here we don't have any reserved bits here, and we have the data field. It will be carries 0 to 64 bytes of data, and CRC field, it will be the same as the standard frame. Like CRC slot 15 bits, and CRC delimiter will be the 1 bit, and acknowledgement, it will be the same as the standard CAN, and end of frame, it will be the same as the 7 bits of standard CAN, and IFS, it will be the similar to the stand. And identifier is 29 as we discussed, and it is used in the CAN to be data can be transferred up to 64 bytes of data at a time, and it supports larger message identifier. So where we can configure the messages for the specific case use 2 to the power of 29 over 500 million unique message identifiers can be configured, and it is suitable for the more complex system with higher message requirements where larger the address space is needed. So here, the CAN data frame format, to how that can be configured in the standard frame and extended frame, we are going to discuss in detail. So here, the standard frame, it's have the startup frame, arbitration field, control field, data field, CRC field, acknowledgement field, end of frame, and IFS. And here, the startup frame and message identifier, and where the messages will be the 2048, means 2 power of 11. So it will be a part of a 2048 unique messages can be selected for the messages IDs specific to the 11-bit identifier. And we have a IDE. IDE will be a 0 here, and RTR will be 1. And next we have a control field. Control field, we have a reserved for 2 bits, and 4 bits or the DLC where the data will be decided. And so how many bytes of data that we transferred in the frame, that will be selected in that data. Suppose the DLC is 0001, means the 1 byte of data we need to transfer. So here the data field is understand 0001 is the 1 byte of data we need to send. Similarly, if I have a 0010, means as the binary format 0010 is a 2 bytes. So here in the data field, that can understand the 2 bytes of data is transferring from the standard CAN frame. And similarly, we have the CRC field, CRC slot, and CRC delimiter. And acknowledgement field, we have the acknowledgement slot and acknowledgement delimiter. And end of frame, we have the 7 recessive bits. And IFS, it will be a part of the recessive bits. So with the each frame messages that is separated. And we have the extended frame. The extended frame, it have the starter frame similar to the standard frame, and message IDs will be 2 power 29. It will be the 536 millions of the messages can be configured. And we have SRR additionally, means as extended we have the SRR, we don't have it in the standard frame. And we have IDE, and it will be a 1 for the standard. Extended for standard, it will be a 0. And we have a message ID additionally, and control field we have a RTR, reserved, and the DLC, and the data, and the CRC and CRA plus, and acknowledgement, and end of frame. So these are the similar After the control field, the data field, CRC field, acknowledgement end of frame, it will be all are similar for standard and extended. Only the difference is the data and that we are able to configure it. So in the extended, we are able to send the data, 64 bytes of data, and in the CAN standard, 8 bytes of data can be transferred. To understand in detail, we are going to understand what is the main difference between the standard and extended. So here, the standard is the specifically we need to understand the identifier is 11-bit identifier and ID is a 0. And coming to the extended CAN, we have a SRR that will be the 1 and ID will be a 1 and control field it will be a 64 bytes of 4 bits and 2 bits will be the considered as the control bill. There is no reserved in it, and here 64 bytes of data can be transferred. And coming to the bus topology, so CAN protocol supports different types of network topology, including bus or the star configuration. The most common topology is the linear bus topology, where all issues are connected to the single bus networks. So, and each end of the terminal within the two wires junctions, the 120 ohms will be configured at the board ends to avoid the reflections. And what are the main characteristics is the multi-master. So any node on the network can initiate the communication without waiting for the permission of the central controller. If two or more nodes attempt to send the message at the same time, CAN uses a non-destructive arbitration to determine which nodes get the priority. So here the lower identifier will get the higher priority for transferring of the messages, and it is a part of the message oriented protocol and there is no specific address based, so it is completely in the ID based the message will be transferred. The transmitting of the data to understand in detail. And as we discussed, we have three types of errors. So how the three types of errors will be transmitted between the states. So the active or the passive or the buffer. So how that can be identified and how we are able to uh, required data can be make to ensure that bus is synchronized in efficient way. So the types of errors in the CAN, like bit error, so occurs when the node sends a bit and reads the different values on the bus. So the transmitting and receiving side, it have the difference in the bit information, then will be the bit error, and stuffed error, where it detected more 5 consecutive bits. Means like we should have a 5 consecutive bits. If we are able to see there are more consecutive bits like similar to the 5 bits, it will be the part of the bit stuffing error, CRC error. So generally it will be the incorrect messages is transmitted in the bus network. And form error, it occurs if the CAN frame contains invalid data, so towards the end of the frame or the acknowledgement delimiter, so then it will be a part of the form error. And the acknowledgement error, it will be happens when the sender doesn't detect any acknowledgement from the other nodes. And error detection mechanism, so here we have the monitoring. The node checks the bus for the discrepancies, and the CRC checking ensures that data integrity, and bit stuffing is the prevents the synchronization error. Acknowledgement mechanism confirms the message reception, and the error handling in the CAN, error frames are transmitted to notify the node of the error. The transmitter retries sending the messages, and node tracks error count to detect the faulty nodes. And error counters transmit here. We have the transmitter error counter and receiver error counter. So whatever the messages that we transfer from the transmitter to the receiver, it will be the transmitter error counter. whichever that receives the data from the transmitter, it will be the receiver error counter. So where the error counter will be measured the number of the bits of data that is transferred. So error active, it will be the normal operation, and error passive will be the limited operation, and will be the bus of which the node will be disconnected. So coming to the active error, initially the number of the counters will be less than or equal to 127. It will be transmitted from active to passive. So here, if it is a more than 255, then it will be a part of the bus of node, where node will be completely disconnected from the transmission. And we have a debugging tools like CANOE, CAN Analyzer, and CAN Oscilloscope, where the data can be monitored. So these are the CAN errors to understand what are the faults that will be available, and we have some description points, and what will be the causes, and what will be the effect that occurred in the CAN errors. So to understand the bit of failure, once the data is transferred more than 255, that it will be the node disconnected will happen, and we have a wiring issues, and where node stops sending the messages, and we have a bit error. It will be the mismatch between the transmitter and observer bit, and acknowledgement error. So there is no acknowledgement that received by the transmitter, and form error, violation of the CAN frame format, and stuff error. If it is more than 5 consecutive identical bits, it will be detect, and CRC mismatch during the data. Arbitration loss, there is no node losses the priority during the transmission, and overload frame fault, it no node sends overload frame due to the processing delay, and bus arbitration error, conflicts in the ID priority during the arbitration. Bus of CANBus error, it is active or passive or bus offset due to the frequent error. So these are some of CAN errors which able to make it. And CAN protocol versions, we have CAN 2.0a and 2.0b. 2.0a uses the 11-bit identifier. 2.b0 supports both 11-bit and 29-bit identifiers, and we have the CANFD. It is a flexible data rate. So it is introduced to allow higher data rate and larger data payload. CANFD increases the data field due to up to 64 bytes of data, and the transmission speed to the switch to the higher rate due to the data phase of the messages. And we have the higher data rate up to 9 Mbps compared to the CAN protocol. And CANBus application, it is a communication between the ECUs like engine control, airbag, and ABS, infotainment, and others. And industrial automations are used in the factors for communication between the control system and the sensors. And medical equipments, CAN is used in medical devices for reliable communication. And aerospace deployed in avionics and flight control system for data transmission between the subsystems. Advantages of CAN is it is a robust error handling and deterministic communication and cost effective. So here it will be the CAN requires a few wires, and it is a lower cost compared to the other protocols. And scalability, it can easily add and remove the node without any major reconfiguration. And limitation of the CAN is the CAN supports maximum up to 1 Mbps based upon the data that we choose or the length of the cable. The baud rate will be configured, and the limitation here, as we told, like for CANFD, we are able to transmit up to 8 bytes of data here in the CAN, and in the CANFD or other protocols, we are able to configure more number of bytes of data. To transfer more than 8 bytes of the data, we need to use other method called flow control method. With the help of that, we are able to configure it. And coming to the CAN is often used for inter-process communication, sensor data transmission, and real-time control. The microcontroller typically has built-in the CAN controller, while external CAN transfer manages the physical layer. So the major difference between the CAN and LIN is, so the LIN is cheaper, and CAN is used for more critical and higher speed communication, and LIN is a single wire, and CAN it is used for more critical high speed protocols. And compared to the full extent, it is a higher speed than the CAN protocol. And coming to the CAN and Ethernet, so Ethernet will be operated in wired and wireless frame where more bytes of data can be transferred. And CAN, it's standard 8 bytes of data. Depends upon the application or the hardware connectivity that the protocol will be choosing. So these are the some high level info of the difference that is made for the CAN and other protocols. What are the common use cases? So here the vehicle is used applications, powertrain, charges, body control and radar system, industrial missions like sensors and actuators in the automation system, robotics, real-time communication between the control system and actuators.